Hi everyone, my name is Sam Parker and I'll be talking about the propulsion system for this mission. Before I begin, I'd like to introduce the rest of the propulsion's team, Scott McGrail, Tyler Hill, and Tim Price. Okay, next slide please. Let's get started. I should probably preface this. The first chunk of this presentation is going to be focused on the prop system for the orbiter, and I'm going to get to the UPS system in the last few slides. So, starting with the orbiter's propulsion system requirements and drivers, we had a requirement to provide 4.15 kilometers per second of delta V to the orbiter, and the orbits team also asked us to tack on 7.5% margin to that to account for any deep space maneuvers or course corrections that might occur. This large delta V requirement was a really big influence in thruster selection, and also the delta V requirement per burn, because we wanted to make sure that each thruster could complete the entire burn well within its qualified burn time.
Now that is with all thrusters, that 4.5, that's the total delivered delta V?
That's the total delivered delta V, yeah, and most of that's going to be completed by the main engine. And
so the next question is, of that, what part of that is deterministic, or what part of it is statistical? So what is the margin against the statistical part?
The orbits team could probably answer this question better than I can. The question was, I'm sorry.
How much delta V of that 415 is for statistical maneuvers, if you don't know, that are not deterministic, that are not part of the determined flight path that you have to know, you'll have to execute at that value?
So do you mean like course corrections?
Right.
None of that. That is included in the 7.5% margin.
Well, is that the same as that is what it is? I mean, that you,
The 4.15
99%
kilometers per second. 4.15 kilometers per second. That's the nominal, like our best estimate, I guess you could say, for the delta V that we passed from orbits to the propulsion team. Then the 7.5% margin was intended to cover that plus any other unknowns that we had.
but are you saying that the 99% value of the statistical maneuvers to execute the flight path is 7.5% of the orbit to add on?
Yes.
So, whatever, is that only 40 meters per second or something like that?
Yeah.
Is that what it is? Okay. But I suggest you really should present that, break that number into the major, the deterministic maneuvers, which the insertion is one, and you have some deterministic path adjustments on the way to make this thing fit, I guess.
Yes.
So those are all determined, and they're not going to change. And you have a number, that's the deterministic delta V for the entire mission. And then what is your statistical allocation against all the maneuvers you're likely to have to execute for navigation?
Right. Well, we didn't actually get into analysis of that.
So there's been no error analysis of navigating this?
A little bit, since maybe Max, you can speak about that.
We've done sensitivity analysis for like insertion and for the flybys, and like if we're off by X number of kilometers, what's the fuel required to correct after the maneuver once we do checks, and that was all to fit, and that all fits within our 7.5% delta V margin. But I can't say that we've done like a full statistical analysis like you are talking
Well,
about.
but I'd like to think 7.5 is based on something instead of this, and then everything fits within it.
Like I said, we took inaccuracies based upon GNC and based upon it was mostly GNC, and then we could see what extra fuel that we're required to correct, and that was what was built into our 7.5% margin.
Please say the count.
Okay, propellant, all right.
You're gonna need some oxidizer every time. you
Yes.
do this.
Okay, thank you. We'll definitely address that and report to the customer. Some of the other drivers that influenced our decisions, power availability. This was a big one. It was one of the deciding factors in our decision to not incorporate electric propulsion into our system, and I'll talk a little bit more about that on the next slide. It also influenced the number of thrusters that could be fired at any one time, as well as the number of components in the system that we can have that continuously draw power.
Power capability, right? More than-
Power capability would probably be a better word for it. And the last big driver I want to touch on is thermal. Because the orbiter is operating at such a low temperature environment at Uranus, we were really worried about the propellant freezing in the tanks. For this reason, we chose to avoid using hydrazine as fuel because it has a really high freezing temperature, or relatively high freezing temperature. And I'll also talk a little more about that later. Next slide, please. Okay, so before I get to the current design of the prop system, I want to talk about a few of the options that we considered, but ultimately decided not to go with. The first one being electric propulsion. We tried really hard to incorporate EP into our system. We chose not to for several reasons. The first one being, for the orbiter anyway, it's impossible to capture into an orbit around the planet using only EP, so we would have to have a chemical system on board anyway. Also, like I said before, the power capability of the orbiter couldn't provide enough power to operate an electric thruster. Another thing that we had for a long time was a dual mode biprop system. So we had a bipropellant main engine with monopropellant RCS thrusters, and they all fed off the same fuel tank. But the problem is the RCS thrusters required hydrazine for fuel, and like I said earlier, we wanted to avoid using that because of its higher freezing temperature. So we decided to go with an entire biprop system instead. And the last thing, this was kind of touched on earlier, we spent a lot of time and effort trying to design a propulsion system for the probes. But because of the complexity in maintaining the stability of the probes on entry while the thruster is firing, we decided that we probably didn't have enough time to solve all the problems and complications with that, given the amount of time we had left to complete the project. So we ultimately scrapped that option as well.
Why would you want it?
At the time we were considering that option, we didn't have a UPS vehicle. At that point in the architecture, we had one orbiter with 3 probes that all left on the same launch vehicle. So 2 of the probes would have to be dropped while the orbiter was orbiting the planet and would require a prop system. So that kind of drove our decision to add the UPS vehicle. Next slide, please. Okay, here's the current design. Over here we have the block diagram of our system, and over on the left, to give you a better idea of what it all looks like when put together, we have the 3D model. As you can see, the system is completely bipropellant with monomethyl hydrazine as fuel and mixed oxide of nitrogen-3 as the oxidizer. The system consists of 10 4-Newton RCS thrusters, 4 200-Newton engines, and 1 3,500-Newton main engine. And I know there were a lot of questions about the 200-Newton engines. I'm going to get into more detail about all the engines in just a couple of slides. Also, you might notice that the system is entirely pressure regulated using helium gas. There are also 2 of almost every valve for redundancy. And there are also 2 normally open pyro valves upstream of all the thrusters, just so that we can latch off one of them should one start to leak for whatever reason, so we can mitigate the amount of fuel that is bled from our system.
So you're not showing valves on the thruster?
No, there are valves. The valves are incorporated within the thrusters. They come with their own valves.
So there's no pyro on the system that represents the 10.0?
No, I don't think so.
Everyone has,
There are two of every time we need a pyro valve, we added a second one for redundancy. Okay. I'm also going to come back to the slide when I talk about the valves a little later on. So next slide, please.
Just
Oh,
go back.
go ahead.
The pyro valves you're showing there, are they normally open, normally closed, or a mixture?
Could you go back to the last slide? Thank you. The ones downstream of the fuel tanks are all normally open, and we have 4 upstream of those tanks to regulate the pressure in. Those are normally closed, and those will be blown right after launch, pressurized tanks.
So the ones down on the main thruster are just to isolate it?
Yeah,
No problem.
in case we have a problem.
And then your latch valves are, you have redundant latch valves there for in case one doesn't work, but you don't have latch valves in series in case one leaks. So, you can always have more latch valves.
Okay, that's a great point. I don't really have an answer for you. But yeah, we'll definitely look into that and address that in our report. Next slide, please. So a little bit about the propellant tanks. We designed the tanks starting with the estimated propellant mass required for the mission. We started from there. We picked a maximum expected operating pressure for each tank, and then using some material properties, we plugged all that into an algorithm for sizing pressure vessels, and that's how we determined the necessary size of the tanks. The helium, or the fuel and oxidizer tanks are both made out of titanium, and the helium tanks are made out of an aluminum core with a composite overwrap for strength. And both the fuel tanks were designed to maintain constant pressure throughout the, did I say that right? Both the pressure in tanks were designed to maintain constant pressure in the fuel tanks throughout the entire mission.
So you designed the fuel tanks just a little bit different than each other. You're not identical. Let me correct. Fuel and oxidizer tanks are not identical.
They were designed in the same manner, and the oxidizer tank's a little bit bigger because of the mixture ratio. The pressure in tanks were designed a little bit different.
Well, the question I've got is, I mean, they're almost the same size, but not quite.
Not quite.
Why didn't you just design one and then just not quite fill the other one up quite all the way full?
I don't think we ever considered that. The rest of the props team, can you help answer that?
I know the volumes are approximately the same. I did kind of consider doing that, but since we were designing the tank, I decided we just designed two. The mass of the oxidizer tank is a lot different, so the tank supports for that are designed differently. So, I mean, it already has to be a separate tank. I mean, I guess we could use the oxidizer tank for fuel, just have more supports than we need, but they are designed separately.
So that makes sense. The problem, I mean, they look pretty close to me, and I don't know how much you saved in mass by doing this. But what you got yourself walked into without realizing it is 2 full sets of drawings, 2 full quals, two sets of tanks that need to be built to qual. You know, and the list just goes on and on and on. So,
2 to 4 sets of spares.
yeah, that too. You know, so you by that one little decision, you've proliferated an enormous amount of engineering activity and hardware without realizing it.
We didn't even think of that. So
That's why I brought it up.
Yeah.
I had a sneaky feeling
that makes a lot more sense.
Yeah.
Actually.
I mean, I know on my spacecraft, I fly identical tanks, and we fill them up just a little bit differently, and that makes life easy.
Okay, thank
You
you.
know, it's the same tank for both of them.
yeah, so I'm guessing you're one optimized.
Yeah, and this may be a place where where you optimize yourself into a disaster.
Okay, so we'll definitely address that in our report to the
Or
customer.
at least $10 million.
At least. Whoops. Okay, next slide, please. All right, here are the engines we've selected. Over here on the right is the table showing some of the specs on the engines. We have one main 3,500 Newton DASA 3SK, which was chosen mainly because of the very high specific impulse it has. And that saves us a lot of fuel since we have such a high delta V we need to provide. We were actually unable to find any engine that had an ISP anywhere near that. The problem with this engine is that it hasn't been made in a very long time, and the company that used to make it was sold to Astrium a few years back. So we would have to have the engine recommissioned and retested and qualified and go through that process, which is expensive and time consuming, and we've accounted for that in our integration and test procedures. In addition to this main engine, we have 4 200 Newton thrusters that, as I mentioned earlier, serve 2 purposes. The first purpose is to act as a backup to the main engine in case it should fail. Should the main engine fail before the Earth flybys, we'll be able to complete the entire mission minus the moon tour, which we have to abort because those 200 Newton engines are slightly less efficient, or quite a bit less efficient than the DASA that we selected. But if we can use the DASA for the first 2 Earth flybys, then it fails, then we can complete the rest of the mission using the backup thrusters.
Have you done the trade analysis of not carrying the big engine?
The big engine?
Yes, same mass, but not using the big engine, not installing the big engine. Is it a better trade that you're not better off just using the 4 200 Newton thrusters?
Yeah, we did. The only reason at this point we still have that big engine in there is because we can complete the entire RFP with any other engine because of its high specific impulse.
And the thrusters are significantly lower in high speed?
Yeah. Over here on the chart, the big engine has an ISP of 352. The smaller SNECMA motors have an ISP of 300. And with such a large delta V and such a massive spacecraft, that's a significant amount of fuel. Oh, and the other purpose of those 200 Newton thrusters is to counteract the torque created by the main engine after the probe is released from the orbiter. This wasn't really talked about earlier, but when the probe is dropped, the center of mass of the vehicle shifts slightly, and the main engine would be creating a torque about that center of mass while it's burning. So to counteract that, we have to fire 2 of the backup thrusters in order to keep them pointed correctly.
So are those pulsed to do this?
I believe so. Those are pulsed? Yes, they are.
And if one of them sticks on or doesn't come on, you're done?
If one of them, the ADCS guys might be able to answer this. If one of them doesn't turn on, we think we can complete the rest of the mission using just the RCS thrusters and one of the other.
Do you have the intelligence on board to recognize that? Do you have what, 6 hours lifetime or something like that?
You're right, it would have to be autonomous. I don't think we've done any analysis for that.
But the idea is, at least from a authority point of view, you can do it 3 out of 4.
Yes.
Have you looked at youngling the main engine?
We have not.
Why not? It was done on Mariner 9 in 1971. And Viking.
Matt, did you answer this? What was this? Why didn't we consider gimbling the main engine?
You have to speak up.
We did not consider that in general. I don't know why. I think that's a broad question.
Yeah, I don't think we can give you a straight answer for that one.
Part of it is also to not have to do, part of it is also not have to do structural elements on the spacecraft. Too, we wanted to minimize any moving deployables, so given like the main cluster would also be another source of concern.
Yeah, but you're introducing a pretty, I would say, complicated system here that could easily cost you the mission. Well, in case, what maybe?
Okay, yeah. We'll have to think more about that one. That's a good point, thank you. Next question. Okay, so here we are back to the block diagram of the system, and over here on the right we have a table showing some of the minor components, mainly the valves and other miscellaneous regulators, thermocouples and whatnot. I just want to add, there are 26 thermocouples scattered throughout the system. We didn't show them on the block diagram because it starts to look really cluttered when we put them all in there, but they're there. And if there are no questions about this, I think we'll move on to the next slide. Okay, one more slide for the orbiter. Here is the propellant budget over here on the right. And on the left, we have the pie chart showing the breakdown of that budget with the amount of propellant used per burn. This pie chart is considering the worst case launch date because the amount of propellant we need to complete the mission changes depending on the date of launch. We size the tanks to carry the propellant for the worst case scenario. In that scenario, notice there's a 11% contingency for this scenario, and if we were to launch an ideal launch date, that contingency would increase to about 20%. And I think we can go to the next slide.
Wait, what about the turbulence? How much haulage do you?
How much ullage?
Oh,
I can't remember off the top of my head. Do you remember how much ullage?
Yeah, initially we designed for 3%, but as the launch window changed around a little bit, we have a 5% ullage. I believe it's 5% in the fuel tank and 4% in the oxidizer.
Next slide, please. Okay, moving on to the UPS vehicle. It has pretty much all the same requirements and drivers as the main orbiter, with the exception that the delta V requirement is far less. We only have to provide about 180 kilometers per second for this vehicle.
Meters.
Meters per second, thank you. And also the Orbits team asked us to account for 50% margin on top of that for this one.
what is that number based on?
Orbits, what was the 50% margin based on?
It is the same sort of thing. The reason this margin is listed as much higher is because those correction burns would be of the same magnitude. They'd be on the order of like 20 or 40 meters per second, but because the total mission delta V is only on 180 meters per second, that's why that margin is listed as much higher.
Does that answer your question? Let's keep going. Next slide, please. Here is the block diagrams for the UPS vehicle over here on your right, and on the left is the 3D drawing. And you might notice we have a monopropellant system for this vehicle with hydrazine as the fuel. And I know I said earlier that we tried to avoid using hydrazine, but because the propellant mass on this vehicle is relatively low, the props team along with the thermal team determined that it would be much easier to actively heat this fuel throughout transit, and also the mission life of this vehicle is quite a bit less than the dimensions for the orbiter. And next slide, please. And this is a list of all the thrusters and tanks on the UPS. We have 12 thrusters in total. 4 Newton thrusters to provide the delta V for the main burns, and 8 1 Newton RCS thrusters to provide the delta V for while the vehicle is 3-axis stabilized. And that also spins up and spins down the vehicle. Also, the pressure tank, we expect that one to be custom made. And we sized it in the same manner that we sized the pressure tanks for the orbiter vehicle. But for the fuel tank, instead of designing our own tanks, we're buying this one off the shelf. We're using a bladder tank. We really wanted to go with the bladder tank because it mitigates sloshing during launch and while the vehicle is spin stabilized and 3-axis stabilized. Next slide, please. And I think we have one more for the prop system, and then we'll move on. This is the burn breakdown for the UPS vehicle. As you might notice, we were able to have 2 launch windows for this mission, for this vehicle. This was a lot easier to do because this one only has 1 flyby. You might notice the first launch window has a much higher propellant requirement, and most of the fuel for each launch window is spent during the initial separation, which occurs right after the vehicles separate from payload attach bin. We conduct a burn to separate them a little bit further so that one arrives about 2.5 years before the other one.
That was a question. So
Yes,
you
sir.
say you have 2 launch opportunities. One has a significant mass savings over the other. Why not pick your second window? Is it purely to have a contingency plan?
Yes, exactly.
As well as the RFP, you can get a launch before December 31st.
Oh, okay.
Okay, that pretty much wraps it up for the prop system. If there are no further questions, we can move on.
Has the
Oh, yes, sir.
customer specified what the navigation accuracy will be? I presume the customer is going to navigate or at least do the orbit determination.
Can someone help me out here? The question was, has the customer provided the navigation for the vehicle?
Who's going to do the orbit determination? And that's your construct there. It's going to tell you where the spacecraft is and when it's going.
Question about the accuracy of the...
Who's going to tell us where the spacecraft is and where it's going? Who's doing the orbit determination?
So we'll be using ranging zones and the Doppler shifts to...
Oh, right. Is this project going to do that? Is this project going to do that, or are they expecting like JPL to take that data and do the orbit determination and tell the project where the spacecraft is and where it's going?
And the customer has to specify the...
The customer will do that. And has the customer told you what the accuracy of that process is going to be so that you can in fact do a statistical propellant analysis?
No, he hasn't.
That would come sometime later.
Yeah.
I think so, yeah. I'm sorry, I don't think we have an answer for it.
Okay, so at this stage, we really don't have any idea how this budget shapes up in terms of actually being able to execute this mission.
Correct.
Okay.
Does anyone else have a comment? Okay, in that case, I have one more subsystem I'd like to talk about. This one shouldn't take too long, it's only one slide. This is the pyrotechnics system. This team consists of myself and Matt McCarty. Next slide, please. We dedicated a small team to manage all the pyrotechnic devices on board the spacecraft. Over here we have just a list of things that we need pyrotechnic devices for, and the table on your left just shows the quantity of the pyro devices. And that's all we really have to say about that. So if there are no further questions, I will pass it on to Stephen Jakowski.
Thanks, Sam. What are you using the pinballs for?
I'm sorry?
What are you using the pinballs for?
The question is, what are we using the pin pullers for?
Okay, so for the pin pullers on the probe are for deploying covers that are on the neutral mass spectrometer and the probe sheet protection.
Oh, you mentioned them. Okay, thank you.
Thank you.
Thanks, Sam.